All right, just a heads up, I had a request. There's supposed to be some folks coming in to talk about a scholarship from the Contractors Association, and they said they wanted to come to 2 classes, and I said they were more than willing to come to mine, but I actually I'm assuming they're coming. They're supposed to come to 2 classes today, and I said, you're more than welcome to come to mine, and but I haven't heard anything as a follow-up, so I'm thinking they're still coming, but I just wanted to mention that. So if we have somebody just randomly come in, that's what it is. Okay, now what we're going to do today is begin a new module, a new topic. Was that me? What was that? Was that an AISC 15th edition steel construction manual? Okay. It was very loud and very thumpy. I'm like, that was a manual. So today what we're going to do is we're going to begin a new module. And this new module is a 2-part module, if you will, because there's one on bolted connections, one on welded connections. But this is going to be the remainder of, or this is going to be the coverage of exam 2. So yeah, this updated course schedule, I was going to talk about I was really going to talk about 2 things. The fact that we had a scholarship presentation, and the fact that I'm not doing homework today. That was my updated schedule. You know how I do homework every lecture. I'm actually not doing homework today, because today I want you to listen, okay? I want you to pay attention, because the thing about bolted connections is that there's a lot of details, and what I want to do is I want to start off today focusing on the details related to strength of bolted connections. There are 2 types of bolted connections, 2 classes that we deal with in structural engineering. We deal with a bearing type connection, and we deal with what's called a slip critical connection. I'll talk about the differences there here in a little bit. What I'm not going to talk about today, because I do not want to risk information overload, is bolt spacing requirements. So how far apart bolts can be spaced from one another, and layout requirements, because I don't want to overload you today. Today I just want you to listen. We'll do a little bit of interactive stuff, and then we'll get into it. Okay, so let's talk about bolted connections. We're going to focus our discussion today on bearing type connections, but we'll get to that here in a little bit. Maybe I should start by talking about bolts. You know, I was humbled and fortunate enough to win a university teaching award one year, and the selection process can be a little rigorous, because in order to do it, you have to sit through classroom visitations of fellow professors at Marshall. And so the way it works is you get nominated during the fall semester, and if you're selected as a finalist for the spring semester, they come in and sit in on your classes. And these are faculty from all across the institutions. There's like nursing professor and English professor and what have you. And so they're coming in and listening to my bolt lectures. And I'm thinking, man, this sounds like a really dry topic. I have weeks of lectures dedicated to bolts. Good Lord, But they seem to find it enjoyable, so who knows. Let's talk a little bit about bolts. So the first thing I want to talk about are the grades, the material grades associated with bolts. So this is an image of a bolt. I'm not sure if it's coming through very clearly on the screen, but typically when you look at a high-strength structural bolt, you tend to find 2 groups of symbols. The first up here says A325. The A325 refers to the ASTM designation. So you know how we've had like A36 steel, A992 steel, and so on and so forth? Well, A325 is a material grade for a bolt, okay? So we have 2 primary types of bolts that we use in structural engineering applications, and those are A325 and A490s. So the difference between the 2 is that A490s are a little bit pricier, but they're a little bit stronger. So dependent upon the day and dependent upon the connection, it might make sense to use A490s versus A325s. We tend to use A490s a lot, for example, in splices in bridge applications, because there's a lot of forces, and so you need a lot of bolts, and so it kind of makes sense to cut the number of bolts, and so you do that by maybe upping the grade a little bit. I should mention A307. Those are sort of like secondary bolts. They're not common in structural applications, but they are referenced in the manual here and there. Now, Like I said, for a structural bolt, there are two symbols. One is A325. The other down here refers to the manufacturer designation, who manufactured the bolt. I'm curious if anybody knows who manufactured this bolt. I did not manufacture the bolt. Given the recent news in the state of West Virginia, who do you think manufactured this bolt? Who's coming to West Virginia? Big steel mill.
On Route 2, I know that, but I don't know what the name of it is.
Nucor. This is a Nucor bolt. So yeah, so you'll find like Nucor or LE for Lejeune or what have you. So those are the manufacturer designations. Now, yes?
What do you mean by secondary members?
Secondary members, like maybe some bracing elements, you know, some stuff that's not structural, like, I don't know, like handrails. And no, nothing that would support main load carrying capacity, like handrail components or stuff like that, like nothing structural. So, or they might be used for temporary bolts, like you're just putting something in there to keep the member up while you lift the crane off for OSHA requirements and whatnot. Nothing super load carrying capacity. Again, they're pretty rare. Any questions? I have a typo.
More expensive than A490.
You're right. That is a typo. We're going to add 0.05 to the mistake counter. This is, yeah.
0.05.
I don't know. I just came up with it. Again, it's a corrupt system. I'm the one that came up with the deductions and whatnot, and I'm the one that manages them. Again, I know it's corrupt. Okay. Now, this is going to sound silly, but this is a standard bolt, and its means of installation is standard. Bolt, washer, nut, you know. There are other means of installing bolts that actually force us to change the geometry of the bolt. Let me give you an example. This is what's called a twist-off control bolt. So you see this a lot in bridge applications where you need a certain prescribed torque to generate your appropriate slip resistance. So the way the bolt works is, so the bolt does not have a hex head on this end. There's no wrench on this end. The way it works is there's this little splined chuck end on this end, and there's these specialized wrenches, and what they do is they grip both the bolt and the nut, and they turn them in opposite directions. And when you hit the specified torque, this little splined end, this little nub on the end sort of chucks off. Have you ever seen this? Have any of you DOH folks seen this? Okay, so it makes the bridge inspector's job easier because whenever they see the splined nut come off, they know that it meets the specified pretension, okay? So these are common in bridge applications for splices and things like that. The thing is that they're actually different bolts. They have different material classifications. So for instance, an A325 or an A490 might now be an ASTM F15 or 1852. Okay, so it's a different material classification according to ASTM, even though the mechanical properties are exactly the same. So it actually has the same, you know, FY or FU value. All the material properties are the same, but it's governed by a different ASTM spec because it's a different bolt. So what AISC does, what the manual does, is it groups all of these common material grades into these groups. So for instance, Group A includes A325, it includes twist-off control bolt F1852, and so on and so forth. And then there's Group B. Group B includes A490, F2280, and so on and so forth. So I want to be crystal clear, there is no such thing as a Group A bolt. Like, you're not going to go to the steel supplier and find a bolt that says Group A or Group B. It's just us as steel designers clumping together all of the bolts that have similar material specifications and saying, we're going to call this Group A and call this Group B, okay? So my point is, sometime in a homework assignment, I might say this is a Group A bolt, and sometime I might say it's an A325 bolt, and you need to know that A325 is in Group A and A490 is in Group B. Group C is a really special classification. Those are some really high capacity bolts. They use that in like seismic land and whatnot, but it's not in common everyday bread and butter structural applications. So does that make sense? Everybody good on that? Okay. Now, let's talk about a bolt assembly, okay? So I got the bolt, the washer, the other washer, the nut, clamping together. Now, if I have a bolt going through a nut, hey, come on in.
Greg, when do you want us to come in?
They come in right now. Come on in.
Give me 30 seconds.
All right. So we're gonna talk here in a little bit about this bolted connection assembly. But one of the things I want you to think about is if you have a plate of steel and a plate of steel, you stick a bolt through it and you tighten the bolt, what happens to the plates? They smack together, right? So there are a lot of forces. I caught the remote. I can't believe that. There are a lot of forces that interact in a given bolt assembly, and I want everybody to think about that, and we'll talk about that here in a second. Gentlemen,
In your class,
the floor is yours.
floor's out. Good afternoon. My name's Gene Thompson. Pat McDonald. We're from the Contractors Association of West Virginia, and we're here to give away money. So is anybody interested in getting some money? We offer a $7,500 scholarship through the Contractors Association. Anybody familiar with the Contractors Association of West Virginia? Well, that's really not good. One, okay. We're an association of highway contractors, building contractors, utility contractors, architects, engineers, associate members, and we are the dominant trade group in the state. We do a lot of political work, and we are here to encourage young men and women like yourselves to consider a career in the construction industry. Anybody thinking about going in the construction business? Or is everybody a civil engineer? What class is this?
This is steel time.
Field, okay. Then maybe somebody's a future bridge builder. So we're looking for young people that are willing to come into our industry. So we're promoting our industry by enticing you with some money to apply for the scholarship. We usually have about 30 engineering students, construction management students across the state apply for our scholarship every year. From that 30 or so applicants, only 30, think about that, only 30, we select a half a dozen or so finalists. You can do the percentage of that. Come for an interview at our offices at the CAWV in Charleston, and if you make that short list of finalists, you won't walk away empty-handed. If you make it to the interview process, more than likely you're going to get some amount of money. Eligible students are sophomores, juniors, and seniors from West Virginia, and we're looking for people who want to stay in West Virginia and become part of the construction industry in West Virginia. Part of the application process is a letter that you'll write to promote yourself as why we should select you for our winner. If you want to be an environmental engineer and go to work in Virginia, that's not what we're interested in. If you want to stay in West Virginia, if you've got contacts in the construction industry, your dad's a carpenter, your mom works in the construction, an operator, maybe you sell something to the construction industry, maybe you work summer intern for a construction, that's what we're looking for. People that are interested in becoming a professional contractor. I'm an engineer by education myself, but I'm a contractor by profession. Professional contractor. That's what I consider myself. But I can't get PC behind my name. You can get a PE, but you'll never get PC. But that's what we're looking for. People who have a civil engineering degree. Everybody's civil in here for the most part? Everybody's civil? Okay. And are interested in actually building things. Construction industry is great. I did it for 40 years. I'm retired now. But you get to drive around and say, I built that. I built that bridge, I did that wastewater treatment plant, I made that cut. You have a lot of tangible things that you put your hands on at the end of your career. It's a lot of fun. You gotta be willing to get up early and go home late. You gotta get mud on your boots. You gotta be out in the field where the work's done. If you want a job where you go in at 8 in the morning and get off at 4 o'clock, do not go to work for a contractor. If you don't mind getting up early and staying until dark 30 or whenever the job takes to get the job done, you might be interested. Who's interested in making the most money when they get out of school? In a career path in the construction industry, you'll make more money in 10 years than you'll ever will working for an owner, a engineering firm, government, anybody else. You'll make more money. 10 years. Why 10 years? Because it takes you 10 years to learn the construction business when you graduate. Maybe you're a little smarter than me and it'll take you less than 10, but that's what it took me, 10 years of hard work to really understand the business. So if you graduate, I'm a civil engineer, I know it all. You go to work for a contractor and you find out you don't know a damn thing. 10 years later, you'll know the business and your value will go tremendously up. Pat's gonna tell you how to apply for it. It's really easy to do. Hope we can encourage some of you guys to do that. Young ladies have done very well at our scholarship. They show the men up a lot of years. I don't know why. They're much more articulate in their letter, and they do a very good job at the interview. So ladies, I encourage you. It used to be when I started in the construction industry, if we saw a woman on a job, what was that? But that's changed, ladies. That's no longer the case. We have women do very well in the industry. I've had several that have worked for me over the years. Great careers. So if you haven't considered the construction business and you're a young lady thinking about graduating here, maybe something to consider. Pat, tell you a little bit about them.
Yeah, so the application process is really easy. Has anybody interned for a contractor DOH in here through the summer at all? Couple? Okay. So I'm sure you've worked with our members out on the site, because our members, if you actually didn't get stuck in the office, our members are the guys that are out working, doing all the road work, the building work, the utility work. And our board is made up, the scholarship board is made up of those members. So as Gene said, you'll come for an interview. If you make it that far, you're going to get to meet those owners. We have a couple of engineering firms represented. Most of them are general contractors, and that's what we are looking for as future members. We have a lot of people that have won this, that either start their own business or move to upper management and have done very well in construction. The application's a one-page fill in the blank. Well, it's two-sided. So Gene mentioned the letter. That's where you're going to need to spend most of the time. So the letter is really when our board's looking at it. So what happens? The applications come in. I think we had 26 last year is what we got. Applications come in. We compile them, send them out to the full board. The board scores the applications. But I will tell you, the letter gets a lot of the people to the interview. So spend a little bit of time on that. If you've interned somewhere, what your extracurricular activities are, if you're involved in concrete canoe or the bridge team, make sure you put all that on there. If you're involved in the engineering club, make sure you put that in there. If you plan on going into construction, or your dad's in construction, or you know somebody that is one of our members, make sure you put that in the letter. Anything you can put in there that'll grab the attention of the one of the scholarship board members will help you get to that level. So Gene said top prize is $7,500. We generally give away about $17,000–$18,000 a year. So if you make the interview process, you're not going to walk away empty-handed. I think the least we gave away last year was $1,500.
1,000 or 1,500.
Yeah. So even if you're finished 6 out of 6 or 7 out of 7, whatever they end up bringing, you'll walk away at $1,500. And our scholarship's a little different because it comes directly to you. Has anybody ever been to Washington Expo? It's been a few years since we've had it because of COVID, but we have the expo every year at the Civic Center. We actually hand out the checks at the Washington Expo. That's coming up March 23rd, 24th. So that's the other thing. Our scholarship's very condensed. You're not going to fill it out now and wait 6 months to hear. What happens is you'll fill it out now. Deadline's March the 4th. That'll go out to the board the next week. Gene will call and schedule interviews. That following week, you'll come for an interview usually on a Friday, and then the next week after that, Expo. So it's a quick turnaround time for that. So and I think we have one of the biggest scholarships now as far as any of the engineering scholarships.
And don't let scholarship, I mean, if you have a 4.0, that's great. We won't hold that against you. But if you don't have a 4.0, that's not the end of the world. I mean, we're looking for people who want to be in this industry and become future dues-paying members of our organization. And you can believe me, that the infrastructure, they just passed this big infrastructure bill. Questionable how much of it is actually for infrastructure, but there's no question that our ports, our airports, our highways, our wastewater treatment, water lines, sewer lines, all need upgrading. And in the next 20 to 30 years, we're going to be forced to spend more money on it. And there's going to be tremendous career paths for young people that want to get into the industry. Because in 20 or 30 years from now, the people that are going to be running these companies that do this work are sitting in this classroom right now. The rest of us, like me, will be retired. So there'll be tremendous opportunities for people in the construction industry. If you like playing with toys, if you like cranes and excavators, you get to play with those toys all the time too. Very demanding career path, but it's a lot of fun. You really enjoy it. I spent 40 years in it, and I wouldn't have traded for anything. So is anybody thinking about the construction industry? Did I convince anybody to think about the construction industry? A couple of things. All right. All right. I don't want to take, we'll be glad to ask any questions. Steel design? Yep. Well, I'll tell you what, designing it is one thing, but erecting it is something else. And that's what contractors have to do. It's easy to draw that on a piece of paper. But if you've got some long old plate girder that's cantilevering out over a pier, you better know how to make that splice either in the air or on the ground before you pick it up and set it. So, important class, especially if you get into bridge building, something you'll use for sure. All right. Any questions?
I'm gonna leave a few applications. I'll just set them on the corner of the desk up here. You can also go to our website, which is on here, and download this. And I'll leave a few business cards too. So if you have any questions, once you start writing your letter, if you have questions, feel free to give me a call or shoot me an email. I'll be glad to help you out with it. You're also going to need a letter of recommendation from one of the professors. All of them here have written it, so they know what we're looking for there. And we will take an unofficial transcript with your application. So you'll need to send that to us. If you make the interview, then I'll need an official transcript. But I know some of the schools have started charging for transcripts, so we quit requiring an official with the application. So,
When is the due date for the submission?
March 4th. So March 4th to get everything to us. And you can email it or mail it. I don't care how it gets to us. I just need to get it by March 4th.
Any questions for anybody? Okay, Marshall has not been well represented the last few years. Aaron Randolph's son was the last time we had a winner a couple years ago, but we have not gotten many applications for Marshall. I don't know what's wrong. We're coming here to promote that. So hopefully some of you guys will jump in there and apply for the scholarship. And if you make it to the interview process, it's really excellent training. I mean, you sit in front of a board of about 6, 8 professional people, ask a lot of questions. It's like a job interview almost. It's really good experience. And the letter writing is good experience. You know, we train engineers to be good engineers, but I've seen a bunch of them that couldn't write a paragraph, don't know how to write a letter. So sitting down and going through that exercise of writing a application letter to apply for the scholarship, it's a good exercise for yourself also. So give it a whirl. All right. Any questions? All right, good luck, guys and ladies.
All right. Back to bolted connections. Okay. So you all have the materials here. You can grab them at your heart's content. But yeah, it's cawv.org. I think it is. So it's
Actual ground workers?
no, like contractors. But contractors have to be on site, is what he's getting at. So, all right, back to bolts. Okay, so if you remember right before the presentation, we were talking about a bolt assembly. And what I mean by a bolt assembly is, you know, we have part A, part B, joined by a bolt. So I said, okay, so if you have part A and part B and you have a bolt going through those parts and you tighten the bolt, what happens to the part? The part joins together, right? So what I have here on this diagram, and I'm going to totally admit that the diagram is incomplete. There's a lot missing from it, and I'll explain here in a second. This is essentially a free body diagram of a bolt assembly. What I have here in blue are the forces that are being applied externally to the bolted connection. So, for instance, as I tighten the bolt, the plates are going to squeeze together, right? Now, from a free body diagram and static standpoint, this is not an equilibrium because I'm missing stuff, right? There's going to be forces going this way pressing the plates together, right? I take a bolt, and I sandwich the plates together. The plates are in compression, and I didn't put that on there. And there's a reason I didn't put that on there, but you'll see this here in a second. Now, once I join these two plates together with a bolt assembly, I'm going to load it, usually, right? So I have a plate, and I'm loading it, right? Think of like a tension member, right? So maybe what I have is I have one plate, and I'm yanking it this way, and one plate, and I'm yanking it that way, right? So the two sort of external forces that are being applied typically are your normal force that the bolt is applying to the plate, and then you have the force that the member is being subjected to. Now the orange forces are what are beneficial in resisting load. Okay. Now we get three sort of resisting forces in a given bolt assembly, dependent upon, or at least three forces that we can count on, dependent upon the class of bolted connections, and we'll talk about that here in a second. So what am I talking about? So here's a marker, here's plate A, plate B, going through, here's the bolt, and I load. So think about how the connection could fail. The first way it could fail is I could just shear the bolt in half, right? I could actually shear the bolt in half. So the resistance offered by the bolt-in shear is one of the resisting mechanisms. Now, if I have a bolt going through a plate and I load, the bolt is actually going to come in contact with the plate, right? Remember, the bolt holes are a little bit larger than the bolt plates, and so as I load, the bolt is going to come into contact. We call that bearing. It is bearing on the plate. So there's actually a bearing force between the bolt and the plate. And so that is a resisting mechanism. We call that bolt bearing. The third resisting mechanism is if I have these plates loaded in compression and I load this way, I seem to remember this whole normal force times the coefficient of static friction tells me I get a frictional force developed between the two plates, right? So there is a friction developed that we can count on. We can only count on it if our bolts achieve a required prescribed pretension according to a given installation method, such as twist-off control bolts, etc. And so we split bolted connections into two main categories. Bearing-type connections are ones that basically we're relying only on bolt shear or bolt bearing. But slip-critical connections are ones that where we are relying on those two mechanisms in it, as well as the friction generated between the two plates. The only time that we can count on or use a slip-critical connection is when we know we have the prescribed amount of pretension. But that prescribed amount of pretension is a little expensive, or a little more expensive, I should say, to install, so there needs to be a good reason for it. We typically only use slip-critical connections in two main arenas. The first is bridges. Okay, let me explain why. How many of you have ever done any type of mechanic work with your hand, fixed a lawnmower, fixed a dirt bike, anything like that? Imagine if you have a loose bolt and you turn on the engine, what happens? It falls off, right? Now imagine if you have a somewhat loose bolt on a bridge that's up for 75 years. See what I mean? Load, unload, load, unload, load, unload for 75 years. You can start to see what's happening, right? So in those instances, under cyclic, any structural engineering application where cyclic loading tends to be a design concern, we tend to utilize slip-critical bolts. The other is earthquake land. There are details there about how we design the connection versus how we construct it and detail it and erect it. But I don't want to get too far into seismicity land. I kind of want to just cover the basics in here. So for bearing type connections can fail in two fashions. Either the bolt can shear or the plate can fail in bearing. But there's actually two ways that can happen. And so for each of these, we're going to have a phi-RN that we can compute. And I want to tell you that for bolt shear, we're going to have a very handy design aid that we can use here in a bit. I'm going to show you that design aid today. We are also going to have connection layouts that we need to meet. We're going to talk about that on Friday. What time is it? 1:35. Okay, let's talk about bolt shear capacity. Bolt shear capacity is a very easy limit to understand. It is a very easy limit to deal with mathematically. It is probably the easiest limit state we will deal with this entire semester. There are two factors that you need to account for. That's the number of shear planes and the thread conditions. Now, unfortunately, at least for the first part, there's a little bit of page turning, but that's going to get a little softer here in a bit. So, before we use any design aids, I want you to follow along with me into a journey of the AISC Steel Construction Manual 15th edition. All right, this is Chapter J. We're going to spend a lot of time in Chapter J over the next few weeks, so get familiar with it. This is Section J3.6. So Section J3 is on bolts. Section J2 is on welds. We're going to talk about both of those in the next few weeks. This is the tensile and shear strength of bolts or threaded parts. We've actually already looked at this once before when we looked at threaded rods. Only now we're looking at parts in shear, not parts in tension. The design tensile or shear strength is computed as Fn times AB. AB is the area of the bolt. We're on 16.1-131. All right. Phi is 0.75. AB is just the area of the bolt, the nominal unthreaded area, and that's important here in a second. Fn is either FNV or FNT. In this case, we're dealing with FNV, the nominal shear stress. Now, there are two looming questions. Are the threads included in the shear plane, and how many shear planes are there? And maybe there's a background question. Dr. Mike, what the heck is a shear plane? Okay, so the shear plane is the line or the plane, if you will, that goes between the plates. Okay, so I want you to look at these two images on the screen. Okay, so I have two bolts that are connecting two plates. The bolt on the left and the bolt on the right have a clear difference, and it is whether or not the threads are included or excluded from the plane between the two plates, or the shear plane. Now, which do you think is weaker, the bolt on the left or the bolt on the right? The left. Why? Because the threads are through the shear plane, right? The threads constitute a component of the bolt that is weaker, okay? Now, you as a structural engineer can specify the bolts that you select such that this doesn't happen. You can actually assume, no, I'm going to spec the bolts so that the threads are excluded from the shear plane. You have the ability to do that as long as you're working with your detailers and whatnot. If you didn't know whether or not the threads were included or excluded from the shear plane, what would you assume? Included, all right? Exactly. Okay, now, we structural engineers are very creative in our naming schemes, so we adopt the following naming convention that you will start to see on homework assignments. So a Group A-N bolt would be a Group A bolt where the threads are included. Group AX bolt would be one where the threads are excluded. Okay, you will start to see that, or I might say A325N or A325X, you know. So instead of referring to the AISC group, maybe I'm referring to the ASTM classification. Either one's fine, okay? So just make sure that you're aware of that. Now, how do we handle that from a design standpoint? We do not consider a different area, we consider a different FNV. Let's go back to this table. We've looked at this table before. Again, I told you we're going to do a journey through the manual today. We're on 16.1-129 now, so one page back. We've looked at this table before when we were looking at threaded rods, only before we were looking at the bottom part of the table. I want to look at the top part of the table. Let's look at this a little bit. So that first row is A307 bolts, and they don't make any distinction about threads included, threads excluded, because you know they're simple enough. All right, look at the yellow rows and the blue rows that I have highlighted. So the yellow rows are group A bolts, the blue rows are group B bolts, okay? Now notice there are two numbers per row. One's for the tensile strength and one's for the shear strength. Notice how the tensile strength is the same for both group A rows and the tensile strength is the same for both group B rows. Why is that? Well, let's read the rows. Let's look at the yellow rows, group A. First one, group A, when threads are not excluded from the shear plane. Group B, when threads are excluded from the shear plane. So why is the tensile strength the same for both of those rows? Because we're talking about shear planes. Tensile doesn't matter, right? So that's why we got the same number for the tensile strength. But look what happens here. So look at the FNV values. When we're dealing with group A bolts, we have 54 KSI for threads included, 68 KSI for threads excluded, right? So the bolt gets stronger when the threads are excluded, right? So these are the values for group A bolts. These are the values for group B bolts. Does this make sense? Everybody okay with this? Now, the other factor to consider is this. Understanding the shear plane is one thing. Understanding the number of planes is something else. So I have here a lap connection versus a splice connection. And if you look at the splice connection below, we have two shear planes, right? We have two planes that the bolt is passing through. So what happens is our capacity is doubled, okay? Now, it does not mean that the bolt magically got stronger under the presence of two shear planes. What it means is that to fail the bolt in shear, we have to rip through more area of bolt, right? So it doesn't, again, the bolt didn't magically get stronger, but the area increased. So single shear, double shear, those are common instances. I have seen one, I was working on a bridge in Ripley, West Virginia, where there was a bolt in triple shear. It was like the only instance I've ever seen that. It was like a truss, and there was a floor beam framing into a gusset plate connection, and there was a lot of plates going on there. So here's a quick exercise. What is the design resistance of an A324 or A325 3/4 inch diameter bolt in single shear, assuming that the threads are excluded? This is really easy. Phi 0.75. What is FNV? Well, A325, are we group A or group B? Huh? Group A. And if the threads are excluded, what is FNV according to table J3.2? 68 KSI. And dB is 3/4 of an inch. So therefore, phi RN 0.75 is that. What is that? If you brought your Casio FX115 ES Plus or similar scientific calculator. Say it again. So 22.5 kips per bolt. Do I have a second on that? All right, let's check and see if you're right. I'm going to show you one of the most handy design aids in the AISC Steel Construction Manual. This is table 7-1 on page 7-22. So this is in the middle of the manual. This is one of the first design aids that we've used that has some color to it, the ASD and the LRFD color codes. Does anybody remember what color we're going to use, the green or the blue? The blue. We are always going to use the blue numbers. Now, what did you say? 22.5? Let's look at this. Group A. What was that last problem we just did? Threads included or excluded? Excluded. Was it single shear or double shear? Single. What was the diameter? Well, by golly gosh gee, look at that. 22.5 kips per bolt. What do you think I'm going to say about this page? You should tab this page. We're going to be using this page quite a bit. In fact, I will never ask you to compute the capacity of a bolt again. Just use that. So all you need to know is the diameter of the bolt. You need to know whether or not we're in single shear or double shear, threads included or excluded, what group you're in. It's a lookup. You can probably generate this in Microsoft Excel in about 5 minutes. It's not that hard. It's really not that complicated. This is a really nifty guide. We're actually going to use this region of the manual a lot because if you turn first off the page on the right is the tensile capacity of the bolts, and if you turn the page, you're going to find the slip capacity of the bolts. We'll talk about that later. Any questions? All right, I want everybody to watch this up here because we're going to call it after this. We're going to talk about bolt bearing capacity. So bolt bearing capacity is when the plate is under consideration. This is when we're not talking about the bolt failing, but we're talking about the plate failing, okay? Because the bolt is coming into contact with the plate, and so the plate could fail as well. There are two ways that the plate can fail in real life. The first is tear out. So if you look here at this image on the right, there's actually these segments on the right where we're actually tearing the plate, right? We're actually shearing it there along the plate. The expression that we use is very similar to block shear. It ain't going to look like it, but you'll see what I mean here in a second. The second is bolt hole ovalization. It's what happens when the bolt mashes up against the plate and it sort of like mashes up and plastifies, and so you get this sort of mushed up region where the bolt hole has deformed. And so the formula that we use for this is very empirical. There's no like derivation you can make for it. Now, if we go to the spec, and I'm not going to make you like turn to this. If you can, if you want, but I kind of want you to just follow along with me, especially since we're running short on time. So our phi value is also 0.75, and we have two different events. We have tear out and we have bearing. Now, the two items of consideration is whether or not deformation at the service load is a design consideration or it's not a design consideration. If you don't care about deformation of the bolt hole at the service loads, then you can get by with using a little bit higher capacity. I kind of think you should be caring. I think you should be trying to maintain the geometry of the connection throughout the design life of the structure. So we are going to consider deformation as a design consideration. So we're going to use this expression and this expression. So here's the equation that we end up using. So the nominal capacity is the minimum of these two quantities. And don't worry, by the way, I am going to upload these slides. I know I said I forgot, but they are going to be uploaded. A lot of this stuff should be familiar. So Fu is the tensile stress. T is the thickness of whatever plate that you're considering. So if you're looking at the flange of a W10 by 49, so you use that flange thickness for T, whatever plate the bolt is going through. The bolt diameter is pretty easy. Now there's this term L sub C. That's new. We're going to talk about that here in a little bit. That is probably the new one, the new parameter. Fortunately, there's some very plug and chug expressions for it, but that's the new one. LC is what's called the clear distance, the L sub C, the clear length between plate materials. So let me show you what that means. What is the deal with LC? LC is the distance between the edge of the hole and either the edge of the plate or the edge of the next adjacent hole. So I've got here a plate that's being yanked in tension, and so I'm going to use some notation. I'm going to say that S is the bolt spacing. I'm going to call this term LE the edge distance. LE is the distance from the center of the hole to the edge of the plate. So everybody watch up here. So if this is S and this is LE, then these are the clear distances from edge to edge, edge to edge. So this is the edge distance minus half a hole diameter, and this is the bolt spacing minus a hole diameter, because you go a half and a half. But here's a little quirk though, and you're going to hate me on this. We're actually looking at the physical dimensions of the plate, the physical dimensions of the hole. If you remember, you add 1/8 of an inch for 2 reasons. One of them is the physical dimensions of the hole. The other is to account for that damaged material and its effectiveness in transferring load to the whole member. But we're actually looking for the physical dimensions of the hole. So in this instance, and in bolted connection land, we do not add 1/8 of an inch. We add a 1/16 of an inch. I know you don't like me on that, but that's just the truth. When we look at a connection, we classify the number of edge bolts and the number of interior bolts. So if you're looking at a connection and you yank on it, these are the edge bolts, these are the interior bolts. So the way we would compute bolt bearing capacity is we compute the bearing capacity of an edge bolt and an interior bolt. And then for the whole connection, we might say there's 4 edge bolts, 16 interior bolts, just sum it up, and then adjust by fee as necessary. And finally, if you actually look at the equations, this first one, this 1.2 LC-TFU, really what we're doing is just like a mini block shear check, because the 1.2 is actually 2 times FU times this area times 0.6. So that 0.6 is buried in there because it's in shear. Questions? I'm going to stop there. I've information overloaded you probably enough today. We're going to exercise this stuff on Friday. That's all I've got, everybody. I will see you all on Friday.
I